Electricity wasn't invented until 1746. But if we discovered it and other effects so long ago, how did we ever come to understand it or do anything with it? Today in this video we will be discussing the concept of Maxwell's equations in a much more interesting way than this video assignment ever intended to be. So, in order to appeal to our low attention spans, we must get started right away before we lose interest. Put forward in 1862 by James Clerk Maxwell, Maxwell's equations are a set of coupled partial differential equations that serve as the classical foundation for all of electrical and magnetic systems. Each of the individual equations are mathematical representations, many of the time partially developed by Maxwell himself, a phenomena discovered by other physicists in the field. Maxwell's equations are extremely useful as a succinct unified theory for classical applications regarding electric and magnetic waves and fields. They see a lot of use in electric dynamics for their usage in deriving many equations for electric field and magnetic field intensity waves. They also see a lot of use in our class for their usage in analyzing magnetic topologies and equivalent circuits from transformers. Maxwell's equations can take two forms, as integral and point vector forms. Both generally relate the same quantities with some minor differences. The point vector forms generally has its applications reserved for other fields, so we will primarily be focusing on the integral forms for their usages in this class. To start, Faraday's law is the first of Maxwell's equations. Magnetic induction was discovered in 1830 by the English physicist Michael Faraday, from which Faraday's law was developed by Maxwell to quantify it. Faraday's law mathematically is defined as the closeline integral of electric field is equal to the negative rate of change of magnetic flux. This essentially means that a changing magnetic field equals an induced voltage on the wire. This relationship defines the basis for transformers, inductors, and electrical generators, as well as Kirchhoff's voltage law for unchanging fluxes. Notice in this demonstration how when the magnet is passing through the coil, the voltage changes opposite to the entering polarity and direction of travel of the magnet. When the magnet is static, notice how nothing happens, even when it is inside the coil. Next is Ampere's law. Ampere's force law was discovered by André-Marie Ampère in the 1850s, and like Faraday's law, was later mathematically defined by Maxwell. Ampere's law mathematically is defined as the closeline integral of magnetic field is equal to the current through the path. This essentially means that static current flowing through a wire creates a static magnetic field radially around it. This is similar to the Biot-Savart law, which is just a consequence of symmetry of Ampere's law. This relationship works well with Faraday's law, as the voltage created by Faraday's induces a current, which creates a magnetic field through amperes to counter Faraday's changing magnetic field. Another thing to note is that this law allows us to consider current flowing through capacitors, because the first term represents the displacement current through the dielectric where no current is actually flowing. Notice in this demonstration that as I increase the current passing through the solenoid, the magnetic field increases directly with it. Also notice how when I change the surface to which we consider Ampere's law to include the opposite direction of the current, the total current gets much closer to zero, effectively cancelling each other out. Next is Gauss' electric law. Gauss' law was formulated by Carl Friedrich Gauss in 1835 from his divergence theorem, with his electric law additionally derived from Coulomb's law. Gauss' electric law is mathematically defined as the closed surface integral of electric field is proportional to charge. This essentially means that the charge enclosed by our surface is proportional to the electric field emitting from it. Fundamentally, this just means that charge and its effects are conserved. This relationship is also the basis for Kirchhoff's current law. Notice in this first demonstration that no matter the size area we use for our surface, the amount of charge enclosed remains the same. Then, notice in the second simulation, when the object is inside, none of the lines point in the same direction to counter each other. But when it is outside, the lines point in similar directions, subtracting from each other due to surface orientation. Also notice how line length is generally conserved in different areas of the box. Lastly is Gauss' magnetic law, which while completely different had a similar upbringing to his electric law. Gauss' magnetic law is mathematically defined as the closed surface integral of magnetic field is equal to zero. This fundamentally means that magnetic monopoles are non-existent, and that magnetic flux is conserved. Like Gauss' electric law. Notice in this demonstration that no matter where I put the enclosing circle, the flux is always zero. From what we have seen today, Maxwell's equations help us solve electric circuits, magnetic circuits, transformers, and understand electricity and its effects as a whole. While we are lucky enough that in the context of this class we don't need the mathematical rigor to solve Maxwell's equations problems, it is still extremely important to understand the physical implications of them, as they are the foundations for a lot of the simplifications we use in this class. You should be glad to have them.